Hello, this is Professor Ma, and welcome to the summaries on the sections on parametric equations of line. We're going to describe lines now using vectors, and in particular the geometries of the about vectors. And involve two things. And first one is the vector additions. I want to remind you of that. And so we have the base to tip rule. So if I have two vectors, if I want to add them, one way to visualize is move the vector v, the base of v to the tip of u, then the diagonal across is the u plus v. Notice in these particular ways of doing things, if I were to multiply, change the v by the length, maybe stretch it, and if I do the same thing, the end result will be another vector that sits on the line, the same line, and based at the point, the tip of u. And so if I stretch this, even longer, and then I will just get another vectors on this line. And so that's how we're going to use these geometry to obtain the equation for a line using vector form. And so the second thing we're going to do is how we're going to describe a line pass through the origins. Okay, so in particular, if I have a vector d, and this d stands for directions, and if I want to express the line, all the points on this line, but as in the form of vectors, and that's just t times d, and t is a scalar. I stretch the vectors, elongate it or shorten it. In particular, if I call this line L, okay, L is t times d. Okay. And d is the vectors, and L stands for the line. It's in the vector form. Okay. In fact, this is going to be called a vector equations. Okay. And in this case, t is called a parameters. And if I were to separate the x component and y component out separately, that I will call this set x, t, y, t as a set of parametric equations describing this line. Now, suppose I have a point somewhere else, and I want the line in the same directions, but the passing through that point P, that it is very easy to obtain an equation for that. And so P is another point, and then the line passing through P in the same directions of D. It's just going to be this, what we call this a vector equation. The point P plus the directions, the stretch direction vectors. So if I change the point, if I change number T, I change different points on this line L. And so in particular, this is the set of parametric equations. Okay. But on the other hand, this again, then if I write this line in this form, then that is we call the vector form of the line L, or vector equations. And this whole thing generalized into three-dimensional space, I would say. So here are some examples. The 2 and 3, notice, goes in front of the coefficient for t. And then the 4 and 5 just add them coordinate-wise, x to the x and y to the yt, and that's it. And it's the point D here sort of serves like a slope, and the point P is another point. So this is a slight different variations of xt and yt parametric form in coordinates. And if I'm given 2 points, then here's the way to write the parametric equations of the line passing through the 2 points. First, find out the standard direction vector. That's so subtract these two vectors. Okay, it doesn't matter which way you subtract, and I have the directional vectors. And now, and then once I have a directional vector, it's kind of like the slope. And I have a point. It doesn't matter which point you use. I can write down a set of parametric equations. Okay, I'm using 0.45 here. Okay. And similarly, here is a line passing with 4, 5 with slope 1/2. This is old problem saying equation of lines, but here's another version of it. The directional vectors, okay, I want the slope 1/2, so that I want a line with slope 1/2, and in particular, I can just choose one, 2, 1. That has slope 1/2, passing through the origins in standard notation, in the standard position. And all I have to do is multiply this vector by t, stretch it, and add it to the point p, move it. Okay. Three-dimensional case, exactly the same thing. And here are some visualization in three-dimensional space. I'll be stretching a vector in three-dimensional space, multiplying by scalar t. And if I want to move to that point, then that will define a line in the space, passing through the point P in the same direction as D, SD. I have the parametric equations and the vector equations, okay? And here's an example, you can read that along. And so here's a summary, basically. And you can write L in the vector equation as t times d directions and plus the point P. It's very similar to, if you look at it, think about it closely, this is very similar to the point slope formula, except things are in vectors. Okay, these are directions. And in point slope formula, m is the slope. In particular, in three-dimensional space, I cannot write a single equation in x, y, z to describe the line, because a single equations, if I plot the points, they form a surface. There's not enough information to only define the line itself. And we can create two equations of two planes intersecting at the line. And that's another way to define the line. Okay, and that's it. We'll talk about lines, planes on the next sections. Okay, bye-bye. Have a good day.